At 85,000 feet above the Earth, traveling 3 times the speed of sound, the cockpit window of the SR-71 Blackbird is hot enough to cook a steak. The titanium skin stretches 2 inches longer than it was on the ground. Fuel leaks from every seam, by design. This isn't just the fastest plane ever built. It's a machine that shouldn't exist. The story you've heard about the Blackbird is one of American engineering triumph. Sleek, black, invincible. A technological masterpiece that dominated the skies for 3 decades. But that's the myth. The real story? It's about a small team of desperate engineers who had to buy metal from their enemies, invent new sciences that didn't exist, and build a plane that leaked, expanded, and caught fire just to stay in the air. They had to solve problems that would make modern aerospace engineers weep, and they had to do it before time ran out, before the Soviets closed the gap, before the next U-2 pilot fell from the sky in a ball of flame. This is the story of how the impossible became inevitable. This is the story of the Blackbird. Kelly Johnson was already a legend when the call came. The year was 1960, and Johnson had designed more revolutionary aircraft than most engineers could dream of in 3 lifetimes. The P-38 Lightning, the F-104 Starfighter, the U-2 spy plane, a glider with a jet engine that could touch 70,000 feet and photograph Soviet missile sites with impunity. Johnson's Skunk Works, the secretive advanced development division of Lockheed, had become synonymous with the impossible made real. But on May 1st, 1960, everything changed. Gary Powers, flying a U-2 over Soviet territory, was shot down. The plane Johnson had promised was untouchable had been touched. The Soviets paraded Powers on television, humiliating the United States, exposing the spy program, and proving that the U-2's altitude advantage had evaporated. Soviet surface-to-air missiles had evolved. The sanctuary of 70,000 feet was now a shooting gallery. The CIA came to Johnson with a problem that bordered on science fiction. They needed a new spy plane, and they needed it to fly higher and faster than anything the Soviets could shoot down. Not incrementally higher, not marginally faster. They needed a quantum leap. The requirements read like a fever dream. 90,000 feet minimum altitude, Mach 3.2 cruise speed, and a range of over 3,200 nautical miles. They needed a plane that could cross continents, photograph military installations, and be home for dinner before the enemy even knew it was there. Johnson looked at the numbers and understood immediately what they meant. At Mach 3.2, roughly 2,200 miles per hour, air friction would transform the aircraft into a flying furnace. The skin temperature would exceed 500 degrees Fahrenheit. Aluminum, the material of every aircraft ever built, melts at around 1,200 degrees, but loses structural integrity at 400. At the speeds the CIA demanded, an aluminum airframe would soften like butter left in the sun, warping and failing catastrophically. There was only one material that could survive: titanium. Titanium could maintain its strength at 600 degrees and beyond. It was light, strong, and could handle the thermal punishment of Mach 3 flight. There was just one problem. In the late 1950s, no one had ever built a large aircraft from titanium, not because they didn't want to, because they didn't know how. Johnson assembled his elite team at the Skunk Works, the best aeronautical engineers, metallurgists, and designers in the country. He showed them the requirements, he showed them the preliminary calculations, and he watched their faces as they realized what he was asking them to do. They would have to build the fastest aircraft in history from a metal they barely understood. And they would have to do it in secret, on a deadline that made the word impossible seem optimistic. The team ran the numbers again and again, hoping for a different answer. They didn't get one. At Mach 3, air molecules don't just flow over the aircraft. They compress and slam into the skin with such violence that they generate tremendous heat. Every conventional aircraft material they knew, every sealant, every hydraulic fluid, every rubber gasket would fail. The heat would cook the electronics, it would boil the fuel, it would turn the cockpit into an oven. Johnson had his material. Titanium was the only answer. But there was one problem that made all the others seem trivial. In 1959, there was only one place on Earth with enough titanium to build his plane. And it was behind the Iron Curtain. The Soviet Union controlled approximately 90% of the world's titanium reserves. This wasn't a minor inconvenience. This was an existential problem. The United States was trying to build the ultimate spy plane to watch the Soviets, and the only way to build it was to buy enormous quantities of metal from the very nation they intended to spy on. The irony was so absurd it would have been funny if the stakes weren't so high. The CIA and Lockheed couldn't simply call Moscow and order several tons of titanium. The Soviets weren't stupid. A massive titanium purchase by an American aerospace company would trigger immediate suspicion. So they did what intelligence agencies do best. They lied, obfuscated, and created layers of deniability so thick that even they sometimes forgot what was real. The CIA established a network of front companies in third countries. These shell corporations, with no obvious ties to the United States government or Lockheed, began purchasing Soviet titanium through international intermediaries. The titanium would be mined in the Soviet Union, sold to a company in one country, resold to another company in a different country, and eventually shipped to the United States with paperwork so convoluted that tracing its origin required a conspiracy theorist's corkboard. The Skunk Works team watched shipments of Soviet titanium arrive at their Burbank facility with a mixture of amusement and dread. They were building a weapon of espionage from the enemy's own resources. It was like constructing a sword from your opponent's armor while he watched, oblivious. The metallurgists even discovered that Soviet titanium, with its unique impurities and processing methods, had properties that made it surprisingly well suited for certain high-stress applications. The enemy had inadvertently provided them with exactly what they needed. But the operation was fragile. Soviet intelligence wasn't blind. As shipments continued, questions began to surface. Why were certain intermediaries purchasing such large volumes of titanium? Where was it going? What was it being used for? The KGB started asking uncomfortable questions. Shipments slowed. Some were delayed indefinitely. The Skunk Works team, already working against a brutal timeline, watched their supply chain threaten to collapse. For weeks, titanium deliveries halted, while the CIA scrambled to create new cover stories, establish new front companies, and reroute the supply chain through different countries. Engineers at the Skunk Works rationed the titanium they had, carefully calculating how much they could use for testing versus how much they needed to reserve for actual production. Every failed test, every scrapped component, felt like a small disaster. They were building the most advanced aircraft in history, and they were doing it while praying that the Soviets wouldn't realize they were funding their own surveillance. Eventually, the supply chain stabilized. New routes were established. The titanium flowed again. But the close call had reminded everyone involved just how precarious the entire program was. They had the material. Now they had to figure out how to work with it, and nobody on Earth knew how to do that. Titanium is a beautiful metal, light, strong, corrosion-resistant. It's the kind of material engineers dream about. But titanium is also a nightmare to work with. And in 1959, the Skunk Works team was about to learn exactly how much of a nightmare it could be. The machinists, skilled craftsmen who could shape aluminum with their eyes closed, discovered that their expertise meant nothing. Standard cutting tools disintegrated when they touched titanium. The metal work hardened as you cut it, meaning that the very act of machining made it harder and harder to machine. Tools that should have lasted for hours shattered in minutes. Drill bits snapped, saw blades cracked. The machinists, accustomed to being masters of their craft, found themselves humiliated by a metal that seemed to actively resist being shaped. But the real horror was the welding. Titanium welds cracked mysteriously, failing stress tests for no apparent reason. Engineers would complete a weld that looked perfect, only to watch it fracture days later. They tested different welding techniques, different temperatures, different filler materials. Nothing worked consistently. Entire fuselage sections had to be scrapped. Months of work vanished into scrap heaps. Finally, a metallurgist discovered the problem: contamination. Titanium is extraordinarily sensitive to impurities, and the Skunk Works facility in Burbank was full of them. The tap water contained chlorine. The chlorine contaminated the titanium during welding and washing. At high temperatures, the chlorine reacted with the metal, creating weak points that propagated into cracks. The solution was as expensive as it was absurd. They had to use distilled water for everything. Every rinse, every cleaning, every cooling operation had to use water that had been purified to remove even trace amounts of chlorine. But the contamination problem went deeper. Engineers discovered that even chalk marks, the simple marks they used to annotate parts and measurements, caused contamination. The cadmium in the chalk ink reacted with titanium at high temperatures, creating failure points. Workers had to stop using standard marking tools. They had to wear special gloves. During the summer months in Burbank, when chlorine levels in the municipal water supply increased, workers couldn't even touch the titanium with bare hands. The chlorine in their sweat would contaminate the metal. 6 months into fabrication, a completed fuselage section, representing thousands of hours of work, failed catastrophically during testing. The team was devastated. Microscopic analysis revealed the cause: contamination from the cadmium-plated tools used to assemble it. The cadmium plating, standard on tools for decades, had been leaching into the titanium during assembly. They had to start over, not just with the fuselage section, but with the tools themselves. Custom titanium tools had to be manufactured, tools made from the same material they were shaping, to eliminate any possibility of cross-contamination. The Skunk Works team developed entirely new manufacturing processes, new quality control protocols, new handling procedures. They were inventing a new industrial science from scratch, learning through failure, adapting through desperation. Every mistake cost time they didn't have, and money that made accountants weep. But slowly, painfully, they learned to work with titanium. They learned its moods, its sensitivities, its demands. They became, out of necessity, the world's first experts in large-scale titanium fabrication. Learning to build with titanium nearly broke them. But the real challenge was still ahead: making a plane that could survive its own speed. Imagine building a car that grows 4 inches longer every time you drive it. Imagine designing a boat that leaks when it's docked, but seals itself when it's moving. Imagine creating a structure that's deliberately loose on the ground, but tightens into perfect alignment at operating temperature. That's what Kelly Johnson had to do with the Blackbird. At Mach 3.2, the Blackbird's titanium airframe expands by up to 2 inches in length due to thermal expansion. 2 inches might not sound like much, but in a precision aircraft where tolerances are measured in thousandths of an inch, 2 inches is a chasm. Traditional aircraft are built with tight seals and precise fits. Panels mate together perfectly. Fuel tanks are sealed completely. Everything is rigid, exact, engineered to microscopic precision. Johnson couldn't do that. If he built the Blackbird with traditional tight seals, the thermal expansion at Mach 3 would crack every seal, warp every panel, and tear the aircraft apart. The structure needed room to grow. So Johnson made a decision that seemed insane. He would design panels with gaps that would close as the metal expanded at operating temperature. On the ground, at normal temperature, the Blackbird would be loose, imperfect, leaky. In flight, at 500 degrees, it would seal itself and become whole. The consequences of this decision were immediately visible. When the prototype SR-71 sat on the tarmac at Lockheed's facility, it leaked fuel, not a little, not a slow drip. It leaked continuously, leaving puddles of JP-7 fuel wherever it parked. Military observers, accustomed to aircraft that were buttoned up and sealed, were horrified. They watched expensive fuel stream from the wings and fuselage and demanded to know what was wrong with the plane. Johnson had to explain again and again that nothing was wrong. The plane was supposed to leak. The gaps were intentional. The Blackbird was designed to be incomplete on the ground and complete in the air. It was a design philosophy that violated every instinct of traditional aerospace engineering, and it required a leap of faith that made military brass deeply uncomfortable. Test pilots reported watching fuel stream from the wings during taxi, wondering if they were sitting in a flying bomb. Ground crews followed the Blackbird with mops and absorbent pads, cleaning up the trails of JP-7 it left behind. The aircraft had to be refueled immediately after takeoff, once the airframe heated up and sealed itself. It was inefficient, expensive, and looked like a disaster to anyone who didn't understand the physics. But it worked. In flight, as the Blackbird accelerated to Mach 3, as the skin temperature climbed past 500 degrees, the titanium expanded, the gaps closed, the panels mated together, the fuel tanks sealed, the aircraft transformed from a leaky prototype into a precision machine, held together not by bolts and rivets alone, but by the very heat that threatened to destroy it. During an early test flight, a seal failed catastrophically at temperature. A massive fuel leak erupted at 70,000 feet. The pilot watched fuel streaming from the wing, evaporating instantly in the thin, cold air, leaving a visible contrail of vapor. Multiple warning lights illuminated the cockpit. The aircraft was bleeding fuel at a rate that would empty the tanks in minutes. The pilot descended immediately, slowing down, allowing the airframe to cool and contract, hoping the seal would reseat itself as the gaps reopened. He barely made it back. Engineers realized their thermal expansion calculations had been off by a critical margin. They had underestimated how much certain sections would expand, and the seal design couldn't accommodate the actual movement. They had to redesign seals, recalculate expansion rates, and test again. Every test flight was a gamble. Every landing was a relief. They'd solved the airframe. They'd learned to build a plane that leaked and expanded and transformed itself in flight. But a plane is useless without engines, and the engines the Blackbird needed didn't exist yet. Ben Rich was Kelly Johnson's propulsion genius, and he faced a problem that seemed to violate the laws of physics. Traditional jet engines become less efficient as speed increases. The faster you go, the harder it is to compress and burn air efficiently. At Mach 3, a conventional turbojet would tear itself apart from the heat and pressure, and even if it survived, it would be hopelessly inefficient. Rich needed an engine that became more efficient as it went faster. An engine that could operate as a turbojet at low speeds, but transform into something else at high speeds. An engine that could swallow supersonic shockwaves and turn them into thrust. He needed to reinvent the jet engine. The result was the J-58, a hybrid that engineers called a turbo ramjet. At low speeds, it operated like a conventional turbojet. Air entered the engine, passed through a compressor, mixed with fuel in the combustion chamber, ignited, and exited through the turbine and exhaust, producing thrust. Standard jet engine operation. But as the Blackbird accelerated past Mach 2.5, something remarkable happened. Bypass doors opened around the engine. The inlet spike, a massive cone at the front of the engine, moved forward, precisely positioning itself to capture and manage the supersonic shockwave. Instead of all the air passing through the turbojet core, much of it bypassed the compressor entirely, flowing around it and directly into the afterburner. The engine transformed. At Mach 3.2, 80% of the thrust came from the inlet spike and bypass system. The turbojet core was almost incidental. The J-58 had become a ramjet, a propulsion system with no moving parts in the airflow, using only the ram pressure of supersonic air to generate thrust. This transformation was the key to the Blackbird's performance. Ramjets become more efficient as they go faster. The faster you go, the more the incoming air compresses itself, and the more thrust you generate. The J-58 inverted the normal rules of jet propulsion. It was an engine that wanted to go fast, that became happier and more efficient the closer it got to its limits. But this transformation required precision that bordered on the supernatural. The inlet spike had to move forward and backward in flight, adjusting its position to keep the supersonic shockwave at exactly the right location. Get it wrong by a few inches, and the shockwave would be expelled from the engine in an event called an unstart. During testing, an inlet spike control system failed. The shockwave was violently ejected from the engine, and the thrust from that engine dropped to nearly zero in a fraction of a second. The Blackbird, flying at Mach 3 with one engine producing 34,000 pounds of thrust and the other producing almost nothing, experienced instantaneous asymmetric thrust. The aircraft yawed violently. The pilot fought the controls, feeling like he'd been hit by a telephone pole. The other engine automatically compensated, the inlet spike repositioned itself, and the shockwave was recaptured. The engine restarted, the pilot regained control. But the incident revealed just how delicate the J-58 system was. It was an engine that performed miracles, but it demanded perfection. The inlet spike control system had to be redesigned, made more robust, given redundancy. Every system on the Blackbird was pushed to its absolute limit. and the engines were no exception. The engines could push the Blackbird to Mach 3. They could transform themselves in mid-flight, swallowing shock waves and generating thrust that defied conventional wisdom. But first, they had to figure out how to start them, and that required a chemical so volatile it explodes on contact with air. Triethylborane, TEB, a chemical with a simple property. It ignites spontaneously when exposed to oxygen. No spark needed, no ignition system, just contact with air, and it explodes. For the J-58 engines, which ran so hot that conventional ignition systems were useless, TEB was the solution. It was also terrifying. Each Blackbird carried about 600 milliliters of TEB, roughly 20 ounces, barely more than a soda can. That tiny amount had to last for every engine start, every afterburner ignition cycle, for the entire mission. The TEB was stored in a pressurized tank and injected into the engine combustion chamber in precise amounts. When it hit the air, it exploded in a dramatic green flash, a chemical reaction so energetic it was visible for miles. Each engine start produced that distinctive green flame, a signature of SR-71 operations that became legendary among aviation enthusiasts. Ground crews would watch the green flash illuminate the tarmac, knowing they were witnessing chemistry at its most violent. Pilots would feel the engines roar to life, powered by a controlled explosion that happened dozens of times during a single flight. But TEB was dangerous. Spills were catastrophic. During ground operations, a technician accidentally spilled a small amount of TEB on the tarmac. It ignited immediately, creating a fire that spread across the concrete. The crew barely escaped. New safety protocols had to be developed. TEB handling became a carefully choreographed procedure, with every step designed to minimize the risk of accidental exposure to air. The limited TEB supply also created operational constraints. If a pilot had trouble starting the engines, if weather conditions were wrong, if the start sequence was interrupted, if anything went wrong, each failed attempt consumed precious TEB. Use up all 600 milliliters, and the aircraft was grounded until it could be serviced and the TEB tank refilled. Pilots learned to treat engine starts with reverence, knowing that every green flash brought them closer to being stranded. The TEB system was emblematic of the Blackbird itself, brilliant, dangerous, operating at the absolute edge of what was possible. Every start was a small miracle. Every flight was a testament to engineers who had learned to weaponize chemistry in service of speed. They could start the engines, they could fly at Mach 3, but there was still one problem. The Blackbird generated so much heat, it needed a way to cool itself, and they found it in the most unexpected place. At Mach 3.2, the Blackbird is a flying furnace. The leading edges reach 600 to 700 degrees Fahrenheit. The cockpit glass exceeds 600 degrees. The titanium skin averages 500 to 550 degrees. The engines generate enormous heat. The electronics generate heat. The hydraulic systems generate heat. Everything is hot, and heat is the enemy. Heat warps metal. Heat destroys electronics. Heat kills pilots. Traditional aircraft use dedicated cooling systems, air conditioning units, liquid cooling loops, heat exchangers that add weight and complexity. The Blackbird couldn't afford that. Every pound of cooling equipment was a pound that wasn't fuel or cameras or range. The engineers needed a cooling solution that was already on the aircraft. They found it in the fuel itself. JP-7 fuel, specially developed for the Blackbird, had remarkable thermal properties. It could absorb enormous amounts of heat without vaporizing or exploding. The engineers realized they could use the fuel as a heat sink. Before the fuel flowed to the engines to be burned, they would circulate it through heat exchangers around every hot component on the aircraft. Fuel flowed through heat exchangers wrapped around the engines, absorbing heat from the turbine casings. It flowed through exchangers in the avionics bay, cooling the electronics that would otherwise fry at altitude. It flowed through the hydraulic system heat exchangers, preventing the hydraulic fluid from boiling. It even flowed through the cockpit environmental system, providing air conditioning for the pilots who were sitting in a titanium oven. By the time the fuel reached the engines, it had absorbed heat from dozens of sources and been preheated to over 300 degrees Fahrenheit. This wasn't a problem. It was an advantage. Preheated fuel burns more efficiently. The heat that threatened to destroy the aircraft was being captured and used to improve engine performance. It was a closed-loop system of elegant simplicity. The faster the Blackbird flew, the hotter it got. The more heat the fuel absorbed, the more efficiently the engines burned, the faster it could go. During a test flight, a fuel circulation pump failed. Without circulation, the fuel couldn't absorb heat from the avionics bay. Temperatures spiked immediately. Warning lights illuminated across the cockpit panel. The navigation computer shut down to protect itself. The radar went offline. The autopilot disengaged. In seconds, the Blackbird went from a sophisticated reconnaissance platform to a barely controllable glider at 70,000 feet. The pilot descended immediately, slowing down, reducing the heat load, praying the systems would come back online before something critical failed permanently. As the aircraft slowed and cooled, systems began recovering. The computer rebooted, the radar came back, the pilot regained full control, but the incident demonstrated how critically dependent the entire aircraft was on thermal management. The fuel wasn't just fuel, it was the lifeblood that kept every system alive. Every system was in place. The titanium airframe that expanded and leaked, the engines that transformed themselves, the TEB ignition that exploded on contact with air, the fuel that cooled while it waited to burn. The Blackbird could finally fly. But the real test wasn't whether it could reach Mach 3. It was whether it could survive what the Soviets would throw at it. Over 800 missiles were launched at SR-71 Blackbirds during their operational history. Surface-to-air missiles, air-to-air missiles. Every type of interceptor weapon the Soviet Union and its allies could field. 800 attempts to bring down the black ghost that streaked across their skies, photographing their bases, mapping their defenses, violating their airspace with impunity. Not one hit, not one SR-71 was ever lost to enemy action. Not one pilot was shot down. The Blackbird's perfect operational record wasn't luck. It was physics. At Mach 3.2 and 85,000 feet, the SR-71 was functionally untouchable. Pilots described the surreal experience of watching missile launches from below. The radar warning receiver would scream. The defensive systems officer in the back seat would call out the threat. The pilot would see the smoke trail rising from the ground, accelerating toward them, and would do the only thing that mattered, push the throttles forward. The Blackbird's defense wasn't evasion. It wasn't countermeasures or jamming or clever tactics. It was speed, pure, overwhelming speed. A missile launched from the ground had to accelerate, climb to altitude, and intercept a target moving at over 2,000 miles per hour. By the time the missile reached 80,000 feet, the Blackbird was already miles away, accelerating, widening the gap with every second. Some missiles got close enough that pilots could see them, close enough that the radar warning receiver went from a warning tone to a continuous scream. But close wasn't enough. The missiles would reach their maximum altitude, run out of energy, and fall back to Earth, defeated by mathematics and velocity. The psychological toll on pilots was real, being shot at repeatedly, even when you know you're safe, even when you trust your aircraft completely, creates stress that accumulates over time. Pilots learned to trust the Blackbird with their lives, but they never stopped feeling the adrenaline spike when the missile warning sounded. The Blackbird's invulnerability had strategic implications. Soviet air defense commanders knew the SR-71 was coming. They could track it on radar, they could launch missiles, but they couldn't stop it. The knowledge that American spy planes could overfly their territory whenever they wanted, photograph whatever they wanted, and leave unscathed was a psychological defeat. The Blackbird didn't just gather intelligence, it demonstrated technological superiority in the most visible way possible. For over 3 decades, the Blackbird flew reconnaissance missions over hostile territory. It mapped Soviet missile installations. It photographed North Korean military bases. It tracked naval movements. It provided intelligence that shaped Cold War strategy and prevented conflicts from escalating into nuclear war. And it did all of this while being shot at, targeted, tracked, and never, ever caught. The Blackbird wasn't invincible because it was lucky. It was invincible because Kelly Johnson and his team at the Skunk Works had built a machine that existed beyond the reach of its enemies. They had built a plane that shouldn't exist, using metal from their adversaries, solving problems that had never been solved, inventing sciences that had never been practiced. They had built the impossible. The SR-71 Blackbird was retired in 1998, not because it was shot down, not because it was obsolete, but because satellites had evolved to the point where they could do the reconnaissance job without risking pilots. The Blackbird's perfect record remained perfect until the day the last one landed. Today, SR-71s sit in museums around the world. You can walk up to them, touch the titanium skin, peer into the cockpit, and marvel at the engineering. But what you're seeing is the finished product, the polished legend. You're not seeing the years of failure, the titanium that cracked, the seals that leaked, the engines that flamed out, the tests that failed, the pilots who trusted their lives to a machine that was still being invented as they flew it. The Blackbird story isn't just about speed or altitude or reconnaissance. It's about what humans can accomplish when the impossible is the only option. It's about engineers who learned to work with a metal that fought them at every step. It's about designers who built a plane that leaked on purpose and transformed itself in flight. It's about chemists who tamed explosives to start engines. It's about pilots who flew into hostile territory, watched missiles launch toward them, and trusted that speed would save them. Kelly Johnson and his Skunk Works team didn't just build the fastest plane ever. They redefined what aerospace engineering could be. They proved that with enough ingenuity, enough desperation, and enough willingness to fail and try again, humans can build machines that seem to violate the laws of physics. The Blackbird flew for 34 years. It set speed records that still stand. It gathered intelligence that shaped history. And it never, ever fell from the sky. That's not just engineering, that's defiance. That's humans looking at the impossible and building it anyway. One cracked titanium panel at a time, one green flash of TEB ignition at a time, one Mach 3 flight at a time. The Blackbird shouldn't exist, but it does. And that makes all the difference.